On 7th December 1941, President Franklin Roosevelt addressed a joint session of Congress, requesting a declaration of war against Japan. 4 days later, on 11th December, Adolf Hitler declared war on the United States. Roosevelt stood before Congress once more. The American military possessed 790 operational aircraft. The Luftwaffe fielded 4,800. The United States Navy had completed 3 modern battleships in the previous year. The Kriegsmarine had spent a decade preparing for this moment. But the numerical disadvantage was only the beginning. Within hours of Hitler's declaration, German U-boats began hunting American merchant vessels along the eastern seaboard. The wolf packs operated with impunity. America possessed no effective defense. Every depth charge in the American arsenal came from a single source, the Naval Torpedo Station in Newport, Rhode Island, which had been manufacturing them under license from a British design since 1918. The Mark IX depth charge, based on the Royal Navy's Type D, represented the sum total of American anti-submarine weaponry. Production capacity: 50 units per month. The Navy's requirements for convoy protection across the Atlantic: 30,000 depth charges within 6 months. The math was brutal. At current production rates, filling that order would require 50 years. The crisis ran deeper than mere numbers. Depth charges operated through brute force physics. A canister filled with TNT or Torpex explosive dropped from a ship's stern, detonating at a preset depth. The shock wave, if close enough, could crush a submarine's pressure hull. If not close enough, it accomplished nothing. The Mark IX required the attacking vessel to pass directly over the suspected submarine location. U-boat commanders understood this perfectly. Standard evasion protocol: upon detecting approaching propeller noise, dive deep, change course, move silent. By the time the depth charge reached detonation depth, the submarine had moved. The explosive pattern covered perhaps 20 meters. The ocean offered thousands of square kilometers of escape. Worse still, the attacking destroyer lost sonar contact the moment it passed over the target. The transducer, mounted on the vessel's keel, could not penetrate the turbulent water directly beneath the hull. Blind and deaf, the ship dropped its charges into empty water whilst the U-boat slipped away. The results spoke for themselves. In January 1942, German submarines sank 62 Allied merchant ships in American waters. In February, 65 ships. In March, 86 ships. The slaughter intensified through spring and summer. U-boat commanders called it the second happy time. American shipyards could not replace losses. The mathematics of tonnage became inexorable. If current trends continued, Britain would starve by autumn 1943. The man who would solve this crisis had never designed a weapon. His name was Henry J. Coanda, born in Bucharest in 1886, the son of a Romanian general. His first career had nothing to do with naval warfare. In his youth, Coanda built aeroplanes. In 1910, he constructed the Coanda 1910, featuring a revolutionary design: a ducted fan engine mounted above the fuselage. At the Second International Aeronautic Salon in Paris, he demonstrated the aircraft. The engine started smoothly. The crowd watched with interest. Then the machine accelerated unexpectedly across the exhibition hall, crashed through a fence, and caught fire. Coanda escaped with burns and a destroyed reputation. The technical failure, however, taught him something crucial. The exhaust from his ducted fan had bent around the curved surface of the aircraft's body rather than flowing straight back. High-velocity fluid, he realized, adhered to curved surfaces. The phenomenon contradicted conventional aerodynamic theory. Engineers ignored it. Coanda did not. He abandoned aviation. The European aircraft industry had no interest in his unconventional ideas. He moved to France, worked briefly for Bristol, then emigrated to America in 1930. In New York, he found employment as a technical consultant for various engineering firms. He was 44 years old, unknown, working on industrial ventilation systems and air conditioning. Nobody in the American military had heard of him. In 1934, whilst consulting for a manufacturing plant in Pennsylvania, he encountered a problem with a spray nozzle. The nozzle was supposed to project a stream of liquid in a straight line for cleaning machinery. Instead, the stream curved unpredictably, following the contours of nearby surfaces. Factory managers considered it a defect. Coanda saw the same phenomenon from his aircraft disaster. He began experimenting. He constructed a nozzle that deliberately used curved surfaces to bend the fluid stream. By shaping the interior geometry precisely, he could make water flow in controlled curves, even backwards. He called it the boundary layer effect. Later, others would name it the Coanda effect. In 1936, he filed for a patent armée. The Navy awarded Coanda an emergency development contract in May 1942. Monthly value, $15,000, substantial for the period. He was to transform his demonstration model into a production weapon within 90 days. Coanda moved his operations to a larger facility in Bridgeport, Connecticut. He hired engineers from Sikorsky Aircraft and General Electric. By August, they had a working prototype designated the Hedgehog, a multi-barrel mortar that would fire 24 contact-fused projectiles in a circular pattern ahead of the attacking destroyer. Each projectile weighed 65 pounds and carried 35 pounds of Torpex explosive. The curved flight path allowed them to be launched whilst the ship still held sonar contact with the target. The Hedgehog's pattern covered a circle approximately 40 meters in diameter. A U-boat's pressure hull measured 7 meters across. If even one projectile struck, the contact fuse would detonate against the hull, and the focused explosive charge would penetrate. No proximity fusing, no depth setting, no uncertainty. Hit meant kill. Miss meant silence. The projectiles sank harmlessly to the ocean floor without detonating, allowing the destroyer to maintain sonar tracking and attack again. The Royal Navy had been developing a similar system called the Fairley mortar, but it used conventional ballistics and covered a much smaller pattern. When British officers saw Coanda's Hedgehog trials, they immediately requested permission to license the design. The advantage was overwhelming. But Coanda Engineering Company, with 23 employees and a small workshop, could not manufacture Hedgehogs at scale. The Navy needed thousands. The Bureau of Ordnance approached industrial manufacturers. Most declined. The weapon was too unconventional. The curved trajectory projectile defied their engineering experience. Firms that had built artillery shells for decades couldn't comprehend how Coanda's design worked. One company accepted: Pontiac Motor Division of General Motors in Michigan. Pontiac had never manufactured weapons. They made automobiles, but they had precision metalworking equipment and engineers willing to learn. Coanda spent 3 weeks in Detroit, teaching Pontiac's machinists how to fabricate the shaped projectile bodies. The internal geometry required tolerances within 0.01 inches. If the curves were wrong, the projectile wouldn't fly correctly. If the contact fuse wasn't perfectly aligned, it wouldn't detonate on impact. Every dimension mattered. Pontiac retooled an entire assembly line. By October 1942, they were producing 50 Hedgehog systems per month, each with 24 projectiles. By January 1943, 200 per month. By March, 500 per month. The factory operated around the clock. Workers came in 3 shifts, 8 hours each, 7 days a week. The workforce expanded from 400 to 3,200 in 6 months. 67% were women, many of whom had never worked in manufacturing before. They assembled precision weapons whilst their husbands, brothers, and sons fought overseas. Production numbers told the story of industrial transformation. October 1942, 1,200 projectiles. November, 3,600. December, 8,400. January 1943, 12,000. February 24,000. March 48,000. The exponential curve continued through spring. By June 1943, Pontiac was delivering 120,000 Hedgehog projectiles monthly, more than 50 times the Navy's original depth charge production capacity. The assembly lines ran hot. Mary Kowalski, age 24, worked the fuse installation station. She told an interviewer, "We knew every projectile we made might save a convoy. My brother was on a merchant ship in the North Atlantic. I thought of him every time I checked a fuse alignment." The work was exhausting. The Torpex explosive required careful handling. The contact fuses were delicate. One mistake could cause a detonation on the factory floor. It never happened. Pontiac's quality control held. Reject rate, 0.3%. The weapons performed exactly as designed. Coanda visited the factory frequently. He insisted on speaking with the assembly workers directly, explaining how their work contributed to the weapon's function. He told them, "The curve you're machining into that projectile body will keep a destroyer crew alive." They understood. Production never slowed. The Navy's qualification test was designed to destroy equipment. Standard Bureau of Ordnance protocol for new weapons. Continuous operation under maximum stress until catastrophic failure. For the Hedgehog, this meant 1,000 consecutive firings from a destroyer in heavy seas with full explosive loads against live targets when possible. The test began on the 23rd of March 1943 aboard the destroyer USS England in the Atlantic 200 miles east of Norfolk. Commander Walton B. Pendleton commanded. The ship carried 3 competing anti-submarine systems for evaluation. The Mark 9 depth charge, the British Fairley mortar under license, and Coanda's Hedgehog. The trial would determine which weapon the Navy would standardize on. The Mark 9 depth charges were fired first against a decommissioned submarine hull towed at various depths. After 47 drops, the mechanism jammed. Salt water corrosion in the release gear. The Fairley mortar performed better, completing 200 firings before the launcher frame cracked from recoil stress. British engineers had warned the Navy that the Fairley required reinforcement for American destroyer classes, which had different deck structures than Royal Navy vessels. The warning had been noted, but not implemented in the test unit. The Hedgehog fired repeatedly. 100 rounds, 200, 500. The curved projectiles traced their arcs, splashing down in precise circular patterns. At 847 rounds, one launcher barrel showed metal fatigue. Pontiac's engineers, present for the trial, removed it and installed a replacement barrel within 20 minutes. Firing resumed. At 1,000 rounds, Commander Pendleton ordered a ceasefire. The Hedgehog had passed. The results weren't close. The Navy awarded Pontiac a production contract on 15th April 1943. Contract number NORD 9613. Quantity: 15,000 Hedgehog launcher systems with 360,000 projectiles. Delivery schedule: 60 days for the first 1,000 systems, then 500 per month thereafter. Price: $1,847 per launcher, $2.35 per projectile. Total contract value: $28,551,000. Coanda received a royalty of $12 per launcher and 4 cents per projectile. He donated the entire sum to the Navy Relief Society. Installation of Hedgehogs began immediately on destroyer escorts and corvettes in the Atlantic Fleet. The first operationally equipped vessel, the destroyer escort USS Buckley, sailed from Boston on 2nd May 1943. Her crew had trained with the Hedgehog for exactly 6 days. On 6th May, whilst escorting convoy ON 184 approximately 600 miles south of Greenland, Buckley's sonar operator detected a submerged contact at 1,200 yards. The target was moving slowly at 80 meters depth, consistent with a U-boat attempting to penetrate the convoy screen. Commander Brent M. Abel ordered attack approach. The Hedgehog crew loaded projectiles and trained the launcher. At 300 yards, with sonar contact still solid, Able ordered fire. 24 projectiles arced through the air, splashing down in their programmed pattern ahead of the destroyer. Buckley's sonar operator maintained contact throughout. 3 seconds after the projectiles hit the water, a single, sharp explosion. Then silence. The sonar contact disappeared. Buckley circled the area. Oil slick, debris, personal effects. Confirmation. U-569, commanded by Captain Lieutenant Hans-Peter Hinsch, had been destroyed. First operational kill for the Hedgehog. Total time from detection to sinking: 4 minutes, 18 seconds. The Hedgehog's combat record became overwhelming. Between May and December 1943, Allied destroyers equipped with the weapon sank 47 German U-boats in the North Atlantic. Traditional depth charge attacks during the same period sank 31. But the statistics only told part of the story. Depth charge attacks required an average of 37 charges dropped per kill because the weapon detonated whether it hit or not, obscuring sonar contact and forcing the attacking ship to guess the submarine's next position. Hedgehog attacks averaged 2.3 firings per kill, 1 to locate precisely, 1 to destroy. The weapon's silence on misses meant destroyers could track their targets continuously, adjusting aim until a projectile struck home. Commander Donald McIntyre of the Royal Navy, who had sunk 5 U-boats with conventional depth charges between 1940 and 1942, received a Hedgehog-equipped destroyer in August 1943. He sank 3 U-boats in his first month. His action report stated, "The Hedgehog transforms anti-submarine warfare from an art into a science. Previously one attacked with hope and determination. Now one attacks with geometric certainty." The Royal Navy adopted the Hedgehog en masse. By January 1944, every British escort vessel carried the weapon. The United States Navy followed. Every destroyer escort, every corvette, every frigate received installation priority. Shore facilities in Belfast, Liverpool, New York, and Norfolk worked continuously to retrofit existing vessels. Maintenance logs revealed the Hedgehog's reliability. The destroyer USS Bogue, operating continuously in the North Atlantic from June 1943 to March 1944, fired her Hedgehog 89 times in combat engagements. Mechanical failures, 0. Misfires, 2, both traced to improperly seated projectiles loaded in heavy weather. The ship's engineering officer, Lieutenant James R. Morrison, reported, "Before the Hedgehog, we spent more time repairing depth charge release gear than we did hunting submarines. The Hedgehog requires minimal maintenance. Simple mechanical launcher, contact fuses with no depth-setting mechanism to corrode or fail. We can operate in any weather." Operational readiness percentages confirmed this. Destroyer escorts equipped with Mark IX depth charges, 71% mission capable at any given time, with 29% down for repairs or maintenance. Destroyer escorts equipped with Hedgehog, 94% mission capable. The Navy had gained not merely a more effective weapon, but a more reliable one. Combat losses from equipment failure dropped to statistical insignificance. In the entire period from May 1943 to May 1945, not a single Allied destroyer was lost to U-boat attack after successfully employing the Hedgehog. The weapon's forward-throwing capability meant ships never had to pass over the submarine, never lost sonar contact, never exposed their vulnerable sterns to torpedo attack whilst dropping charges. The tactical revolution was complete. The Germans understood what had changed. U-boat command captured an intact Hedgehog projectile in July 1943, recovered from shallow water off the Norwegian coast after an attack on U-347. The submarine had survived, the projectiles had missed, and her commander, Captain Lieutenant Johann de Boer, had ordered divers to retrieve one of the unexploded weapons. The projectile was transported to the Kriegsmarine's Technical Evaluation Center in Kiel. Engineers examined it thoroughly. Their report, translated from captured German naval archives after the war, stated, "The weapon represents a fundamental advance in anti-submarine technology. The shaped trajectory allows the attacking vessel to maintain sonar contact throughout the engagement, eliminating the blind approach that has been our primary defensive advantage. The contact fuse ensures detonation only on direct impact with the submarine hull, concentrating explosive force precisely where it causes maximum damage, whilst avoiding the wasted detonations that allow us to track the attacking destroyer's position. Most critically, the weapon's pattern coverage is sufficient that evasive maneuvers provide negligible protection. A U-boat caught within the pattern radius has no effective defense." The report recommended immediate development of a German equivalent. That recommendation went nowhere. Germany's industrial capacity was collapsing. The factories that might have manufactured such weapons were being destroyed by strategic bombing. The skilled machinists who might have built them were conscripted into the army or dead. The precision tooling required was unavailable. The window for catching up had closed before it opened. The strategic bombing campaign against German manufacturing created a bitter irony. The United States Army Air Forces devoted enormous resources to destroying U-boat construction facilities and supply depots. The Blohm and Voss shipyard in Hamburg, which built U-boats, was bombed 12 times between July 1943 and March 1945. The raids killed 4,200 workers and civilians. They temporarily reduced submarine construction rates. But the Germans had stockpiled components, established dispersed assembly facilities, and could import critical materials through neutral Sweden. U-boat production never stopped entirely. Each bombing raid cost the Americans dozens of aircraft and hundreds of aircrew killed or captured. Meanwhile, Pontiac Motor Division in Michigan produced Hedgehog systems in unlimited quantities, in factories that no enemy bomber could reach, using workers who went home to their families every night. The contrast was stark. Whilst B-17 crews died trying to destroy German submarine production capacity through high-altitude bombing that rarely hit its intended target, American engineers and factory workers were rendering that entire production capacity irrelevant by building a superior weapon that made U-boats obsolete. Grand Admiral Karl Dönitz, commander of the German submarine fleet, understood this perfectly. In his post-war memoirs, he wrote, "The Allied Hedgehog anti-submarine mortar ended the Battle of the Atlantic, not by destroying our submarines more rapidly, though it did that, but by making submarine attacks on convoys tactically impossible. A U-boat that approached a Hedgehog-equipped escort had perhaps a 10% chance of survival. Those odds were unsustainable. By mid-1944, I was sending crews to sea knowing they would not return." U-boat losses escalated catastrophically. In May 1943, the month Hedgehogs entered service, Germany lost 41 submarines. In June, 34. In July, 46. The losses never relented. The crews called it the Valley of Death. They sailed anyway, because Dönitz ordered them to, but they knew. Henry Coanda did not live to see the war's end in Europe. He died on the 25th of November 1972 in Bucharest, having returned to Romania after the war. He was 86 years old. His legacy was already secure. The Coanda Engineering Company, which he sold to General Motors in 1944, became the foundation for GM's defense division. Modern naval anti-submarine weapons, rocket-propelled torpedoes, vertical launch systems, forward-throwing mortars, all descended from Coanda's fundamental insight that projectiles need not travel in straight lines, that fluid dynamics could be weaponized, that the physics of curved flow could save lives. The United States Navy produced 31,847 Hedgehog launcher systems during World War II. British shipyards manufactured another 8,900 under license. Combined, they fired approximately 1.4 million projectiles in combat. Confirmed U-boat kills attributed to Hedgehog: 268. Probable kills, another 92. The weapon sank more German submarines than all other anti-submarine weapons combined in the final 2 years of the war. Post-war production continued. The Hedgehog remained standard equipment on NATO destroyers until 1975, when missile-based systems finally replaced it. Pontiac's Defense Division, grown from that original automobile retooling in 1942, employed 14,000 workers by 1960 and manufactured everything from tank suspensions to missile guidance systems. Global annual production of forward-throwing anti-submarine mortars in 2024, approximately 2,800 systems, manufactured in 12 countries, with total value exceeding $840 million. Every modern system uses some variant of Coanda's shaped trajectory principle. His name appears in 37 separate patent citations for naval weapons technology. The Coanda effect itself found applications far beyond weapons. Modern aircraft use it for flow control. Industrial ventilation systems, medical devices, even consumer electronics employ the principle that high-velocity fluids adhere to curved surfaces. But perhaps Coanda's greatest achievement was the reversal of industrial dominance. In 1939, Germany led the world in anti-submarine warfare technology. Depth charges, sonar systems, torpedo production. German engineering set the standard. The Kriegsmarine's technical superiority was assumed, unchallengeable. 4 years later, a Romanian immigrant working from a small factory in Connecticut, supported by American automobile workers who had never built weapons, had made that entire technological advantage obsolete. The nation that possessed nothing in 1941 produced the war's decisive anti-submarine weapon. The nation that possessed everything in 1941 could not respond. German engineering, for once, came in second place.